Welcome back. Let us continue our discussion. So we are in week 8 and this is our first lecture. Now in this week we are going to study shear stress distribution. Now if you consider say a simply supported beam and with a rectangular cross section with say point load acting at the middle, then we will see how the shear stress varies across the section. But before that, let us consider a beam which is simply supported, and for this beam so we have UDL acting over the beam. Now the length of the beam is L and EI is also given. And let the cross section be rectangle of dimension B by D. So this is B and the depth of the cross section is B. For this cross section, we have already studied how the bending stress varies over the cross section. And if you recall, we derived the expression M by I is equal to sigma by Y is equal to E by R. And we also defined neutral axis. It is actually the location where during bending the beam section neither experiences tension nor compression, right? So there is no change in length of the fiber along this neutral axis as we go along the longitudinal axis of the beam, right? Okay. Now, what is the curvature? If you recall, curvature is equal to 1 by radius of curvature, right? Okay. Now, before we go into the details of how this shear stress is distributed over this rectangular cross section, let us quickly revisit the bending of beam and let us first find out the relationship between bending moment, shear force, and the load applied. Right. Now, what is the load applied? We have a UDL of say intensity Q of X. Now, let us consider a differential element over a length of say dx. So this length is d of x, and then let us draw the free body diagram of this part of the beam. So let us consider this highlighted section of the beam over a length of dx. Okay. Now for that, let us first draw the free body diagram of this cross section. So we draw the free body diagram first. So we have an element of dx over this. We obviously have the UDL of intensity Qx. So this distance is dx, and on the left hand side we will have some shear force also on the right hand face, and we'll also have bending moment. Okay. So let us mark this section A and say this is B. So it is between A and now on the left hand side, let the moment be M and shear force be V. Obviously, on the right face, we will have V plus the variation of the shear force, which is dV. Similarly, we will have moment M plus variation of the moment over the length dx, that is dm. Right. Now we can satisfy the equilibrium condition. So let us first consider all the forces acting along the vertical direction and sum them up, and the summation will be equal to 0 because of the equilibrium in the along the vertical directions, right? So what are the vertical forces? We have on the left hand side, we have V. So it is going up. Let us consider upward positive. So V is plus, then minus. On the right face, we have V plus dV. And then there is another force. At the top of the beam, we have the UDL of intensity Qx acting downward. And for that, the net force is Qx, that is the intensity of the UDL acting over a length dx. Now this is equal to 0. Obviously, if we open the bracket, then this V will get cancelled. So let us write it down. V minus V, then minus dV, and then minus Q of x times dx, which is equal to 0. So what we get is dV dx is equal to minus Q of x. So we get the first relation, that is between shear force and the load applied. The first derivative of the shear force is equal to the negative of the load applied, and that's the first relation. Okay. Now we can consider the moment equilibrium. So for that, let us consider, say, phase A, and let us consider all the force, all the moments acting about A is equal to 0. Then what we get? Obviously, we'll have M plus dm, which is positive, and then minus M, which is acting on the left face, but it is negative, right? Then minus V plus dV times dx. Obviously, the other shear force V, which is acting over the face A, will not cause any moment, right? But we have this UDL of intensity Qx. And for that, what we have, minus Q of x, dx is the length over which it is acting, times dx by 2, so dx square by 2, and this is equal to 0. Now, obviously, this m and this m gets cancelled. So what we have here is dm minus v dx minus dv times dx minus q of x dx square by 2 is equal to 0. Obviously, this quantity is very small because both dv and dx, they are small, and similarly this also we can neglect. So these two quantities we can neglect because they are very small, almost close to 0. So what we are left with is dm minus v dx is equal to 0. So if we further simplify, what we get is dm minus v dx is equal to 0, and therefore we have dm dx is equal to v. So this is another relation between bending moment and shear force. So if we differentiate bending moment with respect to x, X varies along the length of the beam, and then we get V, right? Now, earlier we derived this expression. If we differentiate V, that is shear force with respect to X, we get negative of the load. So that means what we have, dV dx is equal to minus Q of X, right? Now, if I use this expression here, and then if we differentiate twice the left hand side, what we have dV dx, right? So this expression, we use left hand side, we differentiate with respect to X, so we get second derivative of m with respect to X. On the right hand side we had V, so now we get dv dx. Now this quantity is obviously equal to minus of the intensity of the load, so minus Qx. So what effectively we get, d2m dx2 is equal to minus Q of X. So these are the three relations that are very important for the bending of the beam. If we differentiate shear force with respect to X, we get the negative of the intensity of the load. If we differentiate bending moment with respect to X, we get the shear force at that particular section at X along the length of the beam. And if we differentiate twice the bending moment with respect to X, what we get again is the negative of the load we apply at a location X. Now, these relations we will be using as we progress in this course. Now, with that background, let us start our derivation for the shear stress distribution. So, we have shear stress distributions. Now, again, let us consider the same beam with a UDL so this is say Q of X, and then again the length of the beam we have L, and also EI of the beam is given, right? So we know the cross section, we know the material property for this beam. Now, let us consider a cross section which can be rectangular, but let us consider a different cross section. So this is the cross section of the beam, and we have neutral axis. So this is the neutral axis, and if you mark the neutral axis along the length of the beam, so this is the location of the neutral axis along the length of the beam, and once we locate the neutral axis, we can also mark YC, that is the distance of the extreme fiber under compression, and then YT. Okay. Now, again, for this cross section, let us consider a differential element. So we have this length dx, and what we do, we again will consider the distribution of shear force and bending moment over this differential element, right? Okay. So we have again on the left hand side we have shear force, say V. On the right hand side we have, say it is going downward. So V to V plus dV. And then again we will have moment here, right? This is say M, and on the right face we'll have M plus dm. Sorry, there is a small typo here actually because the beam is under sagging. So obviously it will bend like this. So this will be tension and the section above neutral axis will be in compression, right? Okay. Now, if we draw the bending stress distribution, say we have neutral axis somewhere here, then obviously we'll have a linear variation, right? Similarly, on the right face, if we draw the bending stress, we get a linear variation over the neutral axis. Now let us consider only the upper part of the neutral axis. We can also extend it to the lower part and we can complete the diagram, but for the time being we are not interested about the lower part. So now this bending stress on the left face, say sigma, right? And let us mark, say A, B, C, C, D. Obviously, on the left face, that is over the face AB, the bending moment is M, and we can evaluate sigma is M by I times we have YC. Similarly, on the right face, obviously we will have, say, sigma prime. Sigma prime is what? The bending moment acting at that face. So we have M plus dm divided by I times YC. Obviously, on the right face, because we have additional bending moment, so the bending stress will be more. And now, what we can do, we can consider a very small strip, right? And this area, say, is dA. And it is at a distance of, say, y. Now, before we move further, let us consider fiber, which is here marked red, right? Let us consider the section above this fiber. Now, obviously, from the left face, where we have sigma as the stress, and the right face, where we have sigma prime as the bending stress, then for each phase, we can quantify the amount of force. So we can quantify the amount of force on the face A, say this point is E and this is F. So we can quantify the force acting over AE and force acting over CF, right? For that, Again, we can use this bending stress, and then if we consider a section at a distance and then consider all the sections and sum up all the forces, then we can quantify the force acting on each face, right? Now, obviously, as we move from AB to CD along the length dx, there is an increase in bending moment. Now, the force acting on the face CD over this segment CF obviously will be more than the one acting over AE, just because of this increment in bending moment. Now, this force, which we are going to quantify in a minute, this is an unbalanced force between the face AE and CF. So they must be balanced. So we'll see how this force is balanced, and that will give us the idea of shear stress distribution over the length dx and across this section as we go from top to bottom. Right. Now, for that, let us first quantify what is the unbalanced force over an area dA. So what is the unbalanced force? We can easily quantify. So we have sigma prime times dA minus sigma times dA. So for sigma prime, we can write m plus dm divided by I times y, because this is at a distance y from the neutral axis, times dA minus, we have m by I times y times dA. Obviously, the unbalanced force we get d of m dm divided by I times y dA. This is the unbalanced force as we move from AB to CD. Right. Now, if we find out the total unbalanced force in the compression zone, we have to actually sum up all the forces as we move from neutral axis. Right now we are at y. As we move upward from the neutral axis up to this point, so we have to start from this EF and we have to go up to fiber AC and sum them up. We'll get total unbalanced force. So the total unbalanced force in the segment AC EF, that is above EF. What is that? We can sum the forces and we move, say this point, this is at y1, so y equal to y1 to yc. So for all the layers, if we find out the summation, we can actually also integrate. So at this y level, we can find out the width of the section, and if the width is b times dy is basically the area, so that we can also express and then integrate from level y1, y1 is somewhere here, up to the extreme fiber which is here, yc. Now if you do that, look at this expression here. So we can take this dm by I outside of the summation. So what we have, summation y equal to y1 to yc y times. Now obviously this is the first moment of area of the section marked this red hatch lines about the neutral axis. So let this be Q. So the unbalanced force is dm by I times Q. So what is Q? Q is equal to summation y equal to y1 yc yda, which is nothing but the cross-sectional area A times y bar. So this is the cross-sectional area of ACEF. So we can find out the area of this section, which is somewhere in between, and this is y bar. So we can find out the area of this rectangular section, or if it is a non-rectangular section, then that section here marked, and we can find out where is the CG of that area with respect to the neutral axis, and then that is y bar, and multiply cross-sectional area of this ACEF with y bar, and we'll get Q. Okay. Now, what we have here is the unbalanced force quantified, right? Now, if there is an unbalanced force, obviously, on the face CF, we have additional force, and if that is not balanced by someone, then what will happen? There will be a slide of the hatch section towards left, because on the right face we have extra force going towards left, and that additional force we have already quantified. And now the unbalanced force, so if unbalanced is equal to dm by I times Q. Now if I draw the segment with this unbalanced force, which is acting this way, so this is the unbalanced force. Obviously it will push the segment AE CF towards left, and the segment below will remain in its place, right? So this entire section here is B and here is D, right? Because of this unbalanced force, if it is not balanced by someone, then obviously the segment here will try to move on the left hand side. Now the question is, in reality it doesn't happen that way, at least we do not experience. If a beam is applied with UDL, obviously there will be a sagging deformation, as you can see, and definitely not a segment of the section at the top of the neutral axis slides towards left, right? That means at the interface there is a shear stress, right? So this shear stress actually prevents the movement of the block ACEF. So this is tau. Now what is tau? Tau, or to be more precise, tau at the section EF, right? Tau at the section EF is equal to unbalanced force divided by the area. Now we can easily quantify the area of the cross section. The length we know is dx, and the width at the level EF is say B, if it is a rectangular cross section, obviously that B will remain constant throughout the depth of the section. So we can quantify this area over which tau EF acts is equal to dx times the width B. Now, if that is the case, then we can actually quantify tau EF using the expression of unbalanced force. Let us do that. So, unbalanced force is dm by I times Q divided by area. We have already derived that dx times B. So, what we have? dm dx times Q divided by I times B. Now, at the beginning of today's lecture, we have derived this expression. So, what is dm dx? It is V, right? Then, what we get in place of this dm dx, we can write V. So, effectively what we get, tau EF is equal to VQ divided by IB. So, that's the shear stress acting at a section EF, which is at a distance y, right? We have derived the shear stress at a distance y, right? Now, if we change this location y from the neutral axis, then we can quantify how this shear stress varies along the depth of the cross section, right? So, this is a very important expression. This expression tells us that how the shear stress is distributed over the cross section. Now, remember this V is the shear force acting at the section. Then Q is basically the first moment of area of the cross section above the fiber. In this case, we are considering a fiber at EF. So, Q is the area of the cross section, as you can see here, ACEF. So, the first moment of that area is equal to Q. I is the moment of inertia that is fixed for a particular section, and then this width B is the width of the fiber EF. So, across the section, so that fiber width on, if this is the cross section, so we can find out how much width of this fiber at a distance y from the neutral axis, and that that may vary if it is not a rectangular cross sections. We will see how to derive those expressions and how that parameter actually affects. But once we fix these parameters, we can actually find out the stress acting at the fiber level EF. Okay, so now let us consider a rectangular cross section and let us see how the shear stress varies over the cross section. So let us consider a rectangular cross section. The width of the cross section is B and the depth of the cross section is D. Obviously, the neutral axis will be at the middle of the cross section. So, this is the neutral axis. Now, the extreme fibers YC and YT are at D by 2 from the neutral axis. What we are going to do is to draw the shear stress distribution across the section. Now, for that, what we have already derived, tau is equal to VQ by IB. So, what we do, we again consider section at a distance y. So we consider this area above the fiber at a distance y from the neutral axis. Then what is Q? Q is equal to A times y bar, right? A is the cross-sectional area that we can easily find out. B is the width times we have d by 2 minus y is the depth of the section times y bar. Now, what is y bar? That also we can find out very easily. So, d by 2 minus y is this segment. So, this is d by 2 minus y, and half of this is where the location of the CG of the hatched portion plus y is basically the distance from the neutral axis. So what we have here is d by 4 minus y by 2 plus y. So effectively we have d by 4 plus y by 2. Or other words, we have d by 2 plus y times half. Okay. So now let us consider y equal to d by 2. Then what happens? Obviously, Q is equal to 0, and Q equal to 0 means if you use this expression, tau is also 0. That means if we start at the extreme point here, shear stress is 0, right? Now, if we consider y is equal to 0, that means the entire section above or below neutral axis, right? Then what will happen? Q is equal to B times d by 2 times y bar is d by 4. So that means Q is equal to B d square divided by 8. So tau is equal to V. In place of Q we can write B d square by 8, and then we have I times B. Now in place of I we can write 1 by 12 B d cube times B. So now if we solve this expression, we can actually cancel this B, and then this d square with d cube will have a d in denominator, and then here we have 2 and 3. So effectively we have 3V divided by twice VD. So which is somewhere here, right? So this part is 3V divided by twice VD. We still don't know what is the variation from 0 at the top to 3V by 2s BD at the middle. That we'll investigate in a minute. For that, we have to use the expression of y that we have already derived, and using this y we will find out q, and using that we'll see what is the expression of tau. So for any y we have tau as V times area is B times d by 2 minus y times the CG of the section. So what we have, d by 2 plus y times half. So this entire thing is q divided by, we have 1 by 12 b times d cube, and the width of the cross section is b. Now we have to simplify this expression. So if we simplify, what we have, v times b, and then we have d minus twice y by 2 times, we have d plus twice y by 2, and then we have another half, so we'll have 2 here, then we have b d cube times b, and we have 12 here, right? Okay, so if we simplify, we have 3 here and then 2 here. So effectively what we get, tau shear stress, tau is equal to 3VB times b square minus 4y square divided by twice b square d cube. So we can cancel 1b, and that's the expression of the shear stress. Now in this expression also, if you put y equal to d by 2, obviously this third bracketed term in the numerator will get cancelled. So effectively we'll get tau equal to 0. And if we put y equal to 0, then again we'll get the expression that we have already derived. And in between, what is the variation? If you look at this power of y, it is square, so it is a quadratic variation as we move downward. So that's the variation of the shear stress over the depth of the cross section, right? Okay, so now we have derived the expression for shear stress for a rectangular cross section. Now not always we have rectangular cross section. Let us see what happens if we have a different cross section. So for that, let us consider a I section. And for I section, if you look at the geometry of the section, we have two flanges, one at the top, another at the bottom. And these two are connected by a web. Again, it's a symmetric section, and therefore the neutral axis will be at the middle of the section. So this is the neutral axis. And let the thickness of the flange be TF and thickness of the web be TW. The width of the flange is B, or say capital B, and then the depth of the flange is capital D. So we can quantify the depth of the web. Say this is small d. Small d is capital D minus twice thickness of the flange. Now for this cross section, our objective is to draw the shear stress distribution, right? Now we already know T is equal to VQ by IB. The problem is here we have a change of the width as we move away from the neutral axis. So initially it had width of TW, then once we cross the wave and enter into flange, we have a width of capital B. Now for that, we have to first consider, so consider flange. And let us take a fiber which is here, and let us first consider this part of the area within the flange. What we'll do, we'll first draw the shear stress distribution over the flange, and then we'll come to the wave part, right? Okay. Now, obviously this distance is y, and for this area marked by this hatched line, we can find out Q. What is that? B, which is the width, times d by 2 minus y is the depth, times we have to find out the CG of this section, which is somewhere here. So for that we have d by 2 minus y, that is the depth divided by 2, so half, plus y is the distance of the CG from the neutral axis, right? Okay. So if you simplify this, we have B times d by 2 minus y times we have d by 4 minus y by 2 plus y by 2, right? And then if we take half common, so we'll have d by 2 plus y, so we can write b times capital D square by 4 minus y square, and we'll have a half outside. Okay. Now we can write down the expression of tau. Tau is VQ, V times Q is B times d square by 4 minus y square divided by 2 divided by IB. So further simplification is possible. So V times B times d square minus 4 y square divided by 8i. So that is the expression for shear stress, and again we have a quadratic variation. So if we start from the top at this point, obviously Q is 0 because there is no area above this point. Obviously it starts from 0 and we have a quadratic variation, right? So we have quadratic variation up to the level which is here at the bottom of the flange. Now at the bottom of the flange, what is y? Y is equal to d by 2 minus TF, right? Okay. Now obviously we can evaluate this expression, and if we put that, we'll get this value here, right? This value of V at TF, at the bottom of the TF, right? So the flange part is solved. Now we will focus on the wave part. Okay. So for wave part, again, we have to consider a fiber at a distance y from the neutral axis, and we will see how these expressions vary. So consider wave. And for that again, we have to modify our drawing here. So now we are here and this is y. So we'll consider the area above the line marked at a distance y from the neutral axis, and then for this line we are going to find out the q first. So let us work out q. For q we have two segments. First, the flange part. For that we have width b times tf times the CG. So we divide this into two segments. So the CG of the flange is at a distance tf by 2 from the top. So we have d by 2 minus tf by 2. So that is the first part. For the second part, width is tw and this depth, we can write the expression. So that is d by 2 minus tf minus y. Then we have to multiply this with the CG of the section within the wave part, and for that again we have y plus d by 2 minus y by 2. So it is somewhere here. Okay. So we can simplify this expression. We have b times tf. For tf, we can actually write down capital D minus small d by 2 is equal to tf. So in place of tf, let us write capital D minus small d by 2 times we have capital D plus small d by 4. So we simplify this expression, and in place of that we write this expression. It's a very simple exercise, you can easily check it out. For the second part, we have tw times again d by 2 minus tf. For that we can write small d by 2 minus y times this part within second bracket. You can simplify and it is half times d by 2 plus y. This is again a simple exercise. I leave it for you. You can easily cross verify. So what we have is b by 8 times d square minus small d square plus tw by 2, and within bracket we have d square by 4 minus y square. Okay, so we have the most critical part q, and then we can see the variation, right? For that, let us consider y is equal to d by 2. Now at d by 2, obviously this part will be 0, and for that again we get the expression tau is equal to v times b times d square minus small d square divided by 8I times TW. TW is the width at this level. So this is TW. So when we have y equal to d by 2, then we have this expression. Earlier, when we started from the flange part, instead of this TW, we had B, right? And that's what we derived earlier. So now TW, obviously, B is much bigger than TW. So when we put TW here, our magnitude of the shear stress will be more because we have TW which is smaller and that is in denominator. Obviously, tau will be more. Right. Now, another case when y equal to 0. Right. So if y equal to 0, then the expression of tau is again V times Q. So for Q, here y is equal to 0. So we'll have B by 8 times capital D square minus small d square plus we have TW d square by again 8 divided by we have I times TW, again width is TW, so we have TW in the denominator. Now again this is a quadratic variation. If you look at the expression of Q, so it is quadratic variation, so we'll have, and because we have a symmetric section, that's the distribution of the shear stress. So this is the shear stress distribution. So you can see if we quantify the shear force acting at a particular section, then based on the geometry we can draw the shear stress distribution over the cross section. And it heavily depends on the width over which we are going to evaluate the shear stress. As you can see, where in the flange section, because we have a bigger width B, obviously the shear stress there is very small. The moment we come to the web, because we have a smaller section, obviously the shear stress will be more, so it is more here. So at this section, it is very critical. So when you'll go to the steel design, you'll see how you can use this shear stress distribution to design the welds here. So for I section, if it is a built up section, we apply welds. So these welds are actually designed based on the shear stress at that level. So this is the tau W, and based on this shear stress, you have to design the welds. But in our course, we are only worried about the shear stress distribution over the section, and we now have the shear stress distribution if we have a non-regular section. Earlier we had a rectangular section, and for that the shear stress at the top and bottom, the value of the shear stress is 0 and it is maximum at the middle. Here in this case again we have maximum, tau max is here obviously at the middle. So when you design the web, you have to consider this magnitude of the shear stress because the webs are designed against shear stress. So that you have to consider. And here, because there is a jump within the cross section, and that is reflected here the moment you find out the shear stress and start from the flange, and from flange you go to the web, there is a jump here. Right. Okay. So with that, let us close our discussion today. In the next class, we'll solve some problem and then we will further investigate how this shear stress distribution varies if you have a very generic cross section. That will be discussed as we progress in this course within this week, right? Thank you very much.